presented by Caltech.
All right, so this week is going to be talking about coupled oscillations. And the reason for that is that the world that we look around us is not a single damned force oscillator. Right? Last I checked, there was more stuff going on. Okay? So we try and use our techniques from oscillations that we've done so far and try and understand how one can understand and work out the physics behind coupled oscillations. And everything is coupled around you. Think about, an atomic lattice, for example. Each single atom could be an oscillator, like vibrates and so on and so forth, but atoms talk to one another. There are interaction terms, there are van der Waals forces, Coulombic interactions, strong repulsions, and so on and so forth, right? So there is a bunch of terms which make things oscillate about itself, and these interactions is what makes the world so, bizarrely non-unique and rather bizarrely unique and pretty exciting. In quantum field theory, as I was mentioning in my first recitation, Feynman diagrams are manifestations of interactions. When things talk to one another, you get things like Feynman diagrams come up, which actually show up and give you corrections over just a single harmonic oscillator. Okay? So if atomic lattices are interacting oscillators, everything in the world is interacting oscillators. Right? So we'll try and, of course, work in the macroscopic regime, talk about springs, pendulums, circuits, all those things, and hopefully give you a sense of how these things can really behave. But the key point is that once things interact, the physics of a particular system, of a particular atom or a particular mass in a spring, doesn't only depend on what that particular mass is doing. Our equations so far have always been in one variable, x, the charge q, something else. It's always been one variable and its time derivatives. There has never been a dependence on that variable's evolution on other variables. Okay? So when things talk to one another, it doesn't matter just what you are doing, but also what your friends are doing, right? So everything gets coupled, and the net result is coupled oscillations. Okay? So I could go the usual way every book talks about it. I could start talking about two pendulas. Maybe that's the plural of pendulum, I hope, which are coupled by a spring in between, and you leave them, they go together. So, of course, it's obvious from this fact that it's not a single pendulum. There are two pendulums, or pendula, I don't know, which are coupled by some interaction amongst the two. So depending on what state they are in, there are different forces acting on the two masses, additionally to what the gravitational force would have been. Okay? So I could go about this way and solve for it in the usual textbook sense. But I think when I was an undergrad and I learned this stuff for the first time, I used to be massively confused. What is going on? People would solve it, I would see it for that moment, but it would be gone after that. And I would read this, it just felt very ad hoc, how one would get these so-called normal modes or normal coordinates and so on and so forth. But I realized with age, unfortunately, that there is an algorithmic way of thinking about it here as well. So I want to give you the big picture first, because examples, I'll do enough of them, don't worry, today and on Friday. But knowing what's going to happen as a framework, I think is very, very crucial here, because every problem can be boiled down to that framework. Okay? So what's really going on is the fact that, I'm going to give you the big picture here. We will do an example, but not this for now. So consider n interacting particles, okay? Some n objects which talk to one another. And these particles are talking to one another. There are the additional force fields. There could be gravity, could be electromagnetism. The whole bunch of things can happen. But what really happens is that I can try and look at the equations of motion for each of these n individual particles. Okay? I can take particle 1, I can read out the forces on that particle, which could be external forces like gravity, and forces from these other n-1 particles. Okay? And I can write down an equation of motion for the first particle, x1 double dot, its acceleration, from Newton's second law, F equals ma. And it's some function, let's say some function f1, But it just doesn't depend only on x1. It depends on all the other coordinates, on all the other particles. So it depends on x1, x2, so on to xn. Okay? So the motion of the first particle depends on what the others are doing as well. It's coupled, it's interacting. Okay? Similarly, for the second particle, x2 double dot is some function f2, x1, x2, so on and so forth, xn. Okay? And then go all the way down to the nth particle, so xn double dot is some function fn times x1 of x1 to xn. Okay? Had f1 only been a function of x1, had f2 been a function only of x2, so on and so forth, had fn only be a function of xn, these would have been decoupled particles, right? They just do what they individually are doing. But this coupling in the first equation, that the acceleration depends on what the others are doing, is what makes it coupled. And it makes your life incredibly hard. Solving diff EQs with coupled terms should not be one's pastime, I believe. I mean, it's not the best way to go about life. Things become really hard very, very soon, right? But under the right assumptions, under the right approximations, there is a way of looking at these things in a very beautiful way. So for our purposes for this course, we're looking at small oscillations. And for small oscillations, we're looking at forces which are proportional to the first power of displacement, F equals minus kx, right? So small displacements, so thereby x squared, x cubed, these terms would not contribute much, okay? So my claim is that if my force laws are linear, linear is a very, very key word here. I know people use this word in a very light-hearted spirit. It's linear. Of course it's linear. It's a big assumption. Newton's second law, F equals ma, is a non-linear force law. Like quantum mechanics, which you learn next time for physics 2b, is a linear law of nature. Classical mechanics is non-linear. Of course, x double dots are linear. If you plug a sum, it just picks up into dots of the two sums. But the forces could be non-linear. There could be a force proportional to x squared. So x1 plus x2 whole square is not x1 square plus x2 square. It's not linear. It doesn't like break up in that usual sense. So if my force laws are linear, by which I mean looking at small oscillations, under that situation, I can try and be smart. I can try and look for a way so as to find, so you try and find such variables, call them u1 through un, and each of the u's depends on the x's. Okay, so u1 can depend on x1 through xn, u2 can depend from x1 to xn, all the particles, so on for un from 1 to n. Okay, u's may or may not have a physical meaning. They are just linear combinations of the x1s. So the force laws are linear, and the u's are also linear combinations of x's. Okay? Then magic can start to happen. So before I get there, I must stress the fact that for each of these actual equations of motion, the F equations, there is no notion of simple harmonic motion there, right? It's not x1 double dot is minus omega naught squared x1. It's not going to be looking like that, okay? So there is no notion of harmonic motion. There is no notion of frequencies anywhere here, okay? So at this stage, don't try to say what the frequency is going to be. There is going to be no frequency because frequencies are defined for oscillations, and when there are no oscillations, there are no frequencies. But now here's the magic. If I can construct such variables, u1 through un, which are linear combinations of x1 through xn, such that u1 double dot is minus omega 1 squared u1, u2 double dot is minus omega 2 squared u2, so on and so forth. Un double dot is minus omega n squared un for constant positive omega 1 through omega n. If I can find such variables, play around, plug the variables back in, and work out the double dots for the u's, which should be clear in the sense that if x depend on time, so do the u's. Okay? And if the u's depend on time, I can have double derivatives and their equations of motion. And if this is true for these kind of equations, then you've said that you've decoupled your initial set of n particles into a set of n decoupled oscillators. For today's purpose, we're ignoring damping, we're ignoring forced oscillation. It's only starting from particles interacting. I get to a smarter choice of variables under which it looks like u1 depends only on u1's motion, u2 only on u2, un only on un, and things evolve by themselves. u1 doesn't talk to any of the other u's, and same for all the other u's. Okay? And now here is the crux of everything. Finding these u's is the goal of the next few weeks. Okay? These are what are called normal coordinates. You might say there is nothing normal about them. It might just be the most abnormal thing in the universe. But the word normal is not the way it's normally used. It has an abnormal understanding. So we talk about what the word normal might mean in this context. You know, it's like Netflix. If you only had one account and one person watching it, you can do whatever you want. But if a 4-person, account is shared by like n people, life becomes hard. And then the interaction, you have to work out ways to work around it. It's a whole mess. You could, however, combine yourselves together and watch shows in sync, and then you become decoupled. Okay? You don't care about what the other person is doing. Each screen can be separate, I know. But the point being that there is an intuition behind these things that which coordinates actually are the ones which decouple under the transformation equations. Now you might ask how many normal coordinates are there? It's a matter of fact, it's a matter of understanding that if I have n variables, I change the variables, the number stays the same. Okay? So if I have n degrees of freedom, by that I mean n particles, n oscillators, n masses on springs, n charges in a circuit, it leads to n normal coordinates. N in number. Got a question? Thought our hand somewhere. No? Okay, my bad. So that's what a normal coordinate is. Okay? There is also a notion of normal mode, which is distinct from normal coordinate. And very often in our courses, we use them almost interchangeably. It is not true. Okay? Normal modes are something else. So this whole thing I can rephrase in a different way. So normal modes. So normal modes are those particular oscillation configurations of my n particles. Okay? There are those, the special ones. So there are special configurations of my n particles for n degrees of freedom, such that each of the particle in this special configuration, so each particle in this special configuration oscillates at the same frequency. So these are not generic, these are very, very special. They depend on initial conditions. They are very particular configurations. Like in the pendulum case, if I leave both the pendulas at the same amplitude, then they go in sync. They have the same frequency of oscillation. If I leave them apart, out of sync by the same amplitude, then they go in and out at the same frequency. Okay? So these special configurations of starting the n particles out such that each particle in that configuration oscillates at a particular frequency. And what possible frequencies? omega 1 through omega n. So therefore, there are n normal modes as well. Okay? And what I mean by this is that in a particular normal mode, x1 would go like cosine omega 1t, x2. Okay, let's say this. Let's say this is the mth normal mode, the number n, right? From 1 to capital N. So the mth normal mode, x1 will oscillate at the frequency omega m. x2 will oscillate at the frequency omega m again. x3, x4, so on, xn will also oscillate at the frequency omega m. This is the mth normal mode. And m goes from 1 through. Okay? And I must clarify, these omega 1 through omega m, or the choice of m, whichever mode you want to think about, it's independent of the natural frequency, if that even means anything here. It's independent of the omega u that we discussed last few weeks, the underdamping frequency. It is not the driving frequency, nothing. Omega 1 through omega n are representative frequencies of the collection of n particles. They are the natural frequencies of the collection of particles. Okay? And the whole game is to start in the equations of motion, linearize them, small oscillations, find linear combinations of the variables such that those variables decouple. They all look like individual harmonic oscillators just by themselves. They may or may not have physical meaning, but special configurations of my actual particles, for the initial conditions, such that each of them has the same frequency. That's a normal mode. For n particles, there are n normal coordinates, n normal modes. End of story. We can all wake up. Does that make sense as the big picture idea? We'll do examples now, and we'll use this method step by step, and it'll all make sense. But where we are going to end up, is that clear to everyone? Any questions about that? Whatever comes. This is important stuff, and it's not the most obvious. It's a way of like decoupling differential equations mathematically. It's a way of decoupling particles into individual oscillators physically. So, thoughts? Yes?
Is there like a general way of going from the x to the u part, or does that depend fully on the ascent?
Excellent question. So my answer is I'm going to go the other way around. I'm going to say there's a way to find the normal modes. We will find the normal modes. Once you find the normal modes, then you will look for algebraic relations between them, which can give you normal coordinates. So this is not going to be the most obvious thing. We'll solve the normal modes first. Anything else? All with me, at least on the big picture idea? Excellent. All right, so let's talk about springs. So I have ball, I have 3 springs and 2 masses. So there is spring 1 and a mass, called mass M. Another spring which is different from the first spring, different spring constant. I'm going to make it like a resistor, but it's a spring. You can make sure of that. There's another mass, M. Another spring with the same constant as the first spring and the ball again. Me in my room last night. Okay, let's call this spring constant K, this one as kappa, and this one as K again. Okay? So 2 symmetrical masses of mass M, 3 springs with 2 holes. Okay? Of course, each of the mass depends on what the other is doing, because the other determines the spring's extension in the middle, and therefore it interplays with the motion of the other particle. Okay? So, all right. First step, write down the equations of motion for the n particles. How many particles do we have? How many degrees of freedom? 2. Okay? There must be 2 equations. x1 double dot and x2 double dot, that's the second particle. How do you write them down? Assume that the first particle went over equilibrium by x1. Second particle went over equilibrium, let's say, by x2. You might say springs could be compressed or elongated depending on which one is larger. Assume something. I'm going to, let's say, assume, for my sake of my equations, math is of course consistent. that x1 is more than x2. So what about spring 1? Is it compressed or elongated? Elongated, right? So mx1 double dot for the first particle. There is a force from the first spring. It's elongated, pulls me to the left. So my convention is positive is right, hence minus k x1. X1 is a positive number. It's the extension of the spring over the spring. That's the force of the first spring. What's the second spring's force on the first particle? It depends on kappa, of course. That's the easy part, I can give you that. What about the direction first? Is it going to be left or right? x1 is more than x2. So this one got compressed, elongated by a smaller amount than the compression. Hence the spring 2 is compressed, hence pushes back, and hence the force is on the left. So on the left. And how much is it? Kappa times the net displacement over equilibrium, the positive number, x1 minus x2, because I assume x1 is more than x2. Is that okay with everyone? Any force from the third spring on the first particle? No, it's not connected, hence no force from the third spring on the first particle. Okay. Similarly, what's mx2 double dot? This is going to be quick now. Second spring, x2, compressed, pushes back to the left, minus k, x2. The first spring, how much is it? What is it doing? It's compressed, right, by the same argument, x1 and x2. This is compressed, pushes back. So for this particle, pushes to the right, hence plus kappa x1 minus x2. Any quick question about these equations? Simple spring, yes?
Can you explain again why the middle one is compressed?
Sure, and that's a good question. It's not obvious on the diagram. So depending on what x1 and x2 are, this could be compressed or elongated, right? So this is my natural length of the second spring. If x2 is more than x1, it gets extended. If x1 is more than x2, it gets compressed. So I assumed something, because for the equations it gives me a handle to write them down. So I assumed this, and then question. Thank you. Anything else? You all see it? So where am I? I have these equations now. Two particles, two equations, okay? We barely started, but okay. And as you notice, they're linear equations. They depend on the first powers of x1 and x2. The equation for x1 double dot depends on both x1 and x2. And x2 depends on both x1 and x2. They're coupled, okay? So what you can do is you can try and write them in a more suggestive way. Combine the variables. Okay? So pull the x1s together. So minus k minus kappa. So minus k plus kappa times x1 plus kappa x2. Just combine x1 and x2 individually. Second thing is kappa x1 and minus k plus kappa x2. Okay? Just simple algebra. And therefore, for the x double dots, so x1 double dot and x2 double dot, they are both linear functions of x1 and x2. The mass m gets divided on the right hand side for the x1 x2 double dots. And they are linear equations. And now I appeal to your linear algebra course. I see some worried faces. Don't worry. It's just matrices. It's just matrices. When I do quantum mechanics as my research, it gets hard sometimes, and I can't sleep, and things become weird. I just remind myself, it's just matrices. Honestly, all of quantum mechanics is just matrix multiplication. I gave a seminar like 3 weeks ago, and the title was Demystifying Quantum Mechanics from Matrices to Quantum Gravity. So it just starts with matrices, to be honest. So it's kind of all here in some sense. So I want to express my equations in a compact matrix form. You don't have to. You can go with these clumsy long equations. It's not suggested. Now look at this. I have these two. I make a vector out of them. Maybe I should remove this line, this looks clumsy. I make a vector of x1 and x2 double dots, and they depend on x1 and x2 linearly. So for two variables, there must be a 2 by 2 matrix which multiplies row to the column and gives you each of the rows on the left hand side. So what's my 2 by 2 matrix which gives me my equations of motion from here? Again, writing them down in terms of exponential like decoupled in each equation helps to find the coefficients or the elements of the matrix, the 2 by 2 that I have. So x1 double dot is minus k plus kappa over m times x1 plus kappa over m x2. So my matrix x1 double dot is minus k plus kappa over m x1 plus kappa over m x2. Is the first multiplication clear to everyone? Some of you might feel this is too slow, but we want everyone to be on board with this. Do we all see that this first equation corresponds to my first equation of motion? Second one, what is it? The first term is the term with the x1. It's kappa over m. It's not k, it's kappa. And the second one is minus k plus kappa over m. Okay. So I wrote down my equations of motion for the n particles as a matrix multiplication of n variables, the n by n matrix, giving me n by 1 column of the double dots, right? And I could do this because it's linear. Had this not been linear, linear algebra would not work because the name just says it. Okay. We all see it? Okay. I'm going a little slow again today because once we have this in the bag, Friday is going to be just doing examples, circuits, something. Just do it. It's pretty algorithmic after that. That's my query. Okay. I'm going to call the variable x1 through xn as the vector. So I'm going to call capital X, in this case x1 and x2. If there were n, there would be n components. So my equation now, this is the column. My equation looks like capital X double dot equals, I'm going to call the 2 by 2 matrix as the matrix minus m times x. Okay. So capital X double dot is the vector of little x1 double dot, little x2 double dot. I know my x's get messed up. I hope you can see the difference between the x's stretched and the normal ones. And capital X is just x1, x2 as a matrix. Again, should be suggestive. This looks like a simple harmonic oscillator for matrices. Double dot is minus something times that thing itself. Okay? So this represents something like simple harmonic motion. So now here's the point. We want to decouple these equations and find our normal coordinates or normal modes. So we will see how you do that. Okay. Any questions so far? Because I felt the fact that with our other topics discussed over the last few weeks, dam, forest, some of the examples made sense, but the paradigm didn't, and then people got confused on the homeworks and so on and so forth. So I think going slow for the first time is important, then you pick up speed. So, any questions about the methodology? So where am I now? I'm still here. So the first thing of writing my equations down.
Why is it negative?
Second. By convention.
Okay.
So yeah, thank you. I should have mentioned that. I just put the negative out for two reasons. One, to make it look pretty, that it looks like a oscillating equation, right? Because had there been a plus, it would not be an oscillation equation, right? And the second thing is, as I'll show you, that m is more important than minus m for conventional purposes.
So is M just that matrix by itself?
With a minus sign. Because I don't have a minus out front. So I just take the minus out. So in this language, m is k plus kappa over m minus kappa over m minus kappa over m and k plus kappa over m. Is that okay? And I should mention that in this case, this matrix M turned out to be symmetric. it need not be. If my first mass was different from the second one, M1 and M2, it becomes non-symmetric. Okay? So again, for simplification, we're just using symmetric matrices here. You can do the same thing with asymmetrical ones. We should do it next time. Okay? All right. So we have my equations, the coupled ones. Now, we're going to find our normal modes. Not normal coordinates, normal modes. Okay, repeat after me. Normal modes are special configurations of the n particles for which each particle has the same frequency. That's fine. But you remember this. This is the key point. Honestly, people forget this all the time. I'm asking, what do you do with normal modes? Find configurations. There would be n in number, but start with 1. So again, ansatz, because I know what I want. I know I want each coordinate or each x to oscillate at the same frequency. Some frequency, but the same for all the particles. So my ansatz is that x1 as a function of time is, let's say, some amplitude a1 going to the complex plane. I can come back to the reals by just taking the cosines out of the complex to the I, and my frequency of choice, generically, let's call it omega, okay? Omega t plus some phase phi 1, okay? Again, omega is some number which is undetermined. We want to find that omega for which this becomes a normal mode, okay? This is not the natural frequency of anything, of a particular particle. This is not the driven frequency of anything. It's something we want to determine, okay? What's x2 of t? Some amplitude unknown, depending on initial conditions. E to the I, omega t or some different omega? The same omega, that's the point, you've got to remember that. Omega t, plus some different phase maybe. But the angular speed is omega. So on, xn, function of time is also an, e to the I, omega, same omega, t plus phi 1. Okay? So my ansatz, the key crux is the same frequency which I want to find. So right now omega is still unknown. Okay? And since I have 2 particles in my string system here, I just need 2 of these. Okay? I can be smart about not having to worry about the phases. I can absorb the phase e to the I phi 1, e to the I phi 2, and make the amplitude complex. Just plug it out. I'm going to call this A1 tilde, the tilde meaning it's a complex thing. So A1 tilde e to the I omega t, and this is A2 tilde e to the I omega t. So it looks nicer. You don't have to worry about the phases individually. You can, no one's stopping you, it won't go wrong. I just pull the e to the I phi 1, merged it with the A1, called it A1 tilde. You all see it? So that's my ansatz for the normal mode with frequency omega, which I want to find. Again, as a vector, this is a column, this is a column. It's just concatenating things together, right? I have an ansatz, I have differential equations. Plug it in to find the omega which satisfies it. Same rule every time, okay? Plug it back in the differential equation, which is given by the one up here as a matrix form. That's the easiest one. What's x1 double dot? That's you. x1 double dot? Yes, question?
Sorry, we're plugging the ansatz back into x double dot.
Into the whole equation, this whole thing, yeah. Because this is my differential equation, I want to find omega to satisfy this differential equation. Good. Alright, so what's x1 double dot on the left hand side from my ansatz? Omega squared or minus omega squared? Minus omega squared. I omega, pull down twice, is minus omega squared. This is minus omega squared times the same thing again, so it's x1. Okay. Same for x2, minus omega squared x2. This piece is the x double dot. Okay? Equals the matrix M, the 2 by 2 matrix M. The same that we so minus M. Okay? By convention. And now we'll see why the convention was good. Should write this properly. Equals minus M times x1, x2 again. x1, x2. Is that okay? Okay. Let's plug our ansatz again back in and see what happens. It's making it more explicit. I pull the minus omega square out front. So it's minus omega square. x1, x2 is a1 tilde e to the I omega t, a2 tilde e to the I omega t. E to the I omega t is common for both. Pull it out, e to the I omega t. a1 tilde, a2 tilde. Okay? Equals minus the M matrix times a1 tilde, a2 tilde, e to the I omega t is common. Okay? E to the I omega t is cancelled off. What do I have? The minuses also go away now. And that's why I had the minus with the M. Because this minus cancels the minus omega square from my double derivative, the I square which comes in from the two dots. So now I have M, which is the 2 by 2 matrix, times a1 tilde, a2 tilde equals omega square a1 tilde, a2 tilde. And la-di-da. That's an eigenvalue equation. A matrix M, a 2 by 2, acting on a vector 2 by 1, gives me a constant number times the vector again. Take a minute. Is everyone on board with the fact that this is an eigenvalue equation? Do we all know eigenvalues? At least for this level, that some matrix M, its eigenvector is a column x, such that M times x is a number times the vector x again. Can I get some nods, please? Okay. So what happened? Omega squares. So omega square are the eigenvalues of the matrix M. Okay. So equations of motion. Here in terms of x double dot equals minus a matrix times x. Plug it back, and omega square are just the eigenvalues of the matrix M. And we can find that. How do you find the eigenvalues? So I have a matrix. To find the eigenvalues, that matrix, what do you do? Determinant M minus lambda I equals 0. And lambdas are the eigenvalues. This will be omega squares, but generically, for the matrix M, M minus lambda I is determinant of 0. That gives the eigenvalues. Okay. I think I'm short on time today, but next time I'll also talk a little bit about what do eigenvectors and eigenvalues mean. Everyone has the question when you're young, what does the word eigen mean? What are eigenvectors? I can find them. Any monkey can find them in the sense of just plugging and doing it. But the meaning is what's important here. We talk about that next time. Okay? But algorithmically, let's find them. Okay? Determinant of M minus lambda I, M I have. So determinant, let's do this quickly. A plus kappa over M minus lambda minus kappa over M, kappa. This is a minus kappa over M. This is a K plus kappa over M minus lambda. Determinant vanishes. 2 by 2, multiply this, it's K plus kappa over M minus lambda whole squared minus kappa squared over M squared equals 0. Determinant, solve for it. Lambdas are just the omega squared because they are the eigenvalues of M, as we just proved. Okay? And if you solve for this, it's just a simple second order quadratic equation. Solve for it. What you find is that how many eigenvalues will be there? 2. Which should make sense because there should be 2 independent frequencies. It should lead you to n decoupled oscillators, and hence 2 because I had 2 particles. So omega 1 is square root, and just copy it down, K over M. and omega 2 is square root k plus 2 kappa over n. So I found two frequencies such that if I leave my particles in a certain way, my ansatz, they have the same frequency, either omega 1 or omega 2. Okay? So these are my normal frequencies, and my normal modes are these, which have the same frequency of oscillation.
It's just using positive convention instead of doing plus minus for omega 1 and omega 2.
Omegas are positive numbers because they're frequencies, so they have to be some radians per second. So you take the positive by convention. Yes. Good. Is that okay with everyone? I went super slow today, and I hope we know why. And we see the connections going on in this like bigger picture here. Now, once I have my normal modes, I should also mention you can find the eigenvectors just by plugging it back in here again. For a particular omega, plug the number, get the eigenvector. So the eigenvectors in this case are for some constant a1 times 1 and 1, and you get some constant a2 times 1 and minus 1. Now for this kind of a column, a1 is a number here. This column, if you plug it in the equation, it gives you omega 1. Plug this column in the equation, gives you omega 2. Okay? These are my eigenvectors. Now, so two particles, two solutions, which are the eigenvectors of my coupled equations of motion. Now, again, these were special solutions. These are special configurations which had the same frequency of oscillation. Let's write them down again to write this thing in our heads for once and for all good, for all eternity. It's important. Normal mode 1. So normal mode 1 is x1, x2 as a function of time is this number a1 in the same phase times cosine omega 1t plus phi 1. I took the phase part out again to make it look nice and pretty. Frequency went back to the real plane, it's oscillating with some cosine. Frequency omega 1, that's normal mode 1. Normal mode 2, is when x1 and x2 have some value a2, they're out of phase. So when x1 is at a, x2 is at minus a, a2, it's cosine omega 2t plus phi 2. Now these particular special solutions, these are special, these are not generic. We found them, and these are the normal modes. Okay? Question?
Are A1 and A2 related to the amplitudes, or are those just constants?
So they are constants which are also amplitudes,
Okay.
right? Because cosines go from -1 to +1, and a is the maximum of that.
Okay.
So they are amplitudes, but also constants which get determined by initial conditions. And how many conditions should I have for my initial conditions here? 2, 4. 2 particles, each need 2. So A1, phi 1, A2, phi 2. 4 conditions. Specify that. Okay? But these special solutions say the fact that I started x1 and x2 at the same location, at the same displacement, and they have the same frequency of oscillation. Okay? If I start them in opposite amplitudes, A and minus A, and then they go at the same frequency. Okay? These are special normal modes. And the beauty of math tells me that the general solution for x1 and x2 x1 as a function of time, x2 as a function of time, is a linear combination of my normal modes. In more mathy language, if you remember from linear algebra, the eigenvectors of a matrix with distinct eigenvalues span the space. They are enough to make any vector in that space. You can just add them to make any other vector. So the general solution is E1, 1, 1, cosine omega 1t plus phi. Omega 1 is the first normal frequency, root k over m plus a2. 1 minus 1, the other normal mode, cosine omega 2t. Omega 2 is square root k plus 2 kappa over m plus phi 2. Okay, that's a general solution. By knowing my initial conditions, where is particle 1, where is particle 2, speed of particle 1, speed of particle 2 at time 0, I can find a1, phi1, phi1, a2, phi2. Okay. Normal modes are special because for my normal mode 1, in my general solution, a2 was 0. And normal mode 2 corresponds to a1 being 0. So they are special. Okay? For the general solution, it's just a linear combination of the two. Okay? Let me go on for a minute, then I'll take up more questions about this. So we found generically, if you are confused about what this is really saying, break it up into two parts. Let me do it for you. x1 as a function of time is a1 cosine omega 1t plus phi 1 plus a2 cosine omega 2t plus phi 2. And x2 as a function of time is a2 cos omega 2t plus phi 2 minus a2 because of this minus 1 here, cosine omega 2t plus phi 2. That's all this is saying. Okay? Now, coming to the word normal coordinates. These up there are normal modes. You can put them together, superposition, just simple linear combinations, give you general solutions, of which special cases are normal modes, which is this. Now, normal coordinates. So, maybe I can go here, that people maybe they should also get the benefit of the angle. So, normal coordinates. What are those? Again, back to the algorithm. They are those linear combinations. Okay, question. This is important. Yeah.
Oh yeah. So for the second equation, is the for AT.
Thank you. This is A1.
Oh, it also speaks to the
It's also thank you.
Oh,
Omega
and
1.
the oscillation. Yeah.
There we go. A1 omega 1 phi 1 A2 omega 2 phi 2 A1 omega 1 phi 1 minus A2 omega 2 phi 2. Thank you so much. Yeah, I didn't sleep. I don't ever sleep, I think. See, I'm lost. Yeah, okay, what are normal coordinates? Those are those linear combinations of x1 through xn which look independent. Now, again, I've seen this stuff before, so I'm claiming, so just like look up at these equations. What can you do to x1 and x2 so as to get rid of the omega 2 piece? Because you want a combination which only has a single frequency. What can I do to the equation to only survive the omega 1 terms? Add them. Okay? So u1 is x1 plus x2, and this oscillates at, we add them up together. You can normalize it if you want, doesn't really matter. It's some constant, so it's 2a1 cosine omega 1t plus phi 1. So the sum is one normal coordinate. The other one, u2, has to oscillate at the other frequency. So cosine omega 2t plus phi 2. And to subtract them off, it takes off the first piece. And it's x1 minus x2. And you get 2a2. So these linear combinations are normal coordinates. Okay? I want to dispel a very important myth that I had for the longest time in my life. This got clarified to me like 4 years ago or something, which is bad for a PhD person in theoretical physics. The plus and this minus combination that I had x1 plus x1 minus x2 is not because my eigenvectors were 1, 1, and 1 minus 1. It's tempting to say, 1, 1, add 1 minus 1, subtract. No, it's not that. Okay? Let me show you why. Let's say that I did this whole bunch of stuff for again 2 particles, and I found my eigenvectors to be the following. I found that the frequency omega 1, whatever it was, some number, had the eigenvector proportional to 3, 2, and the second one, omega 2, was proportional to 1 and minus 5. I could have found a matrix M for which eigenvalues were two numbers omega 1, omega 2, for which the eigenvectors look like 3, 2, and 1 minus 5. Of course, there will be some number out front, overall constant, A1, A2, but not the point. The point is that they are what they are. Okay. Now let's see what are the normal coordinates in this situation. First, write down generically x1 and x2. Okay? Alright, please help me here. What's x1 as a function of time? Anything before 3? 1 or something else? 3. Because this is the first part of the first normal mode, has a frequency omega 1. It has a 3A1. Just like I had 1A1 here, I have 3A1 cosine omega 1t plus phi 1 plus, what's the other one? 1A2 cosine omega 2t plus phi t. I hope I got my 1s and 2s correct. x2t. Alright, what is this? 2A1 cos omega 1t plus phi 1 plus minus 5 A2 cos omega 2t plus phi 2. Okay? General solutions are just eigenvectors with their oscillations, put them together, linear sum, superposition. Now, I want to find a u1 and u2 such that the u1 depends only on the omega 1 piece and u2 only on the omega 2 piece. So how do I combine these equations together to do that? So for u1, I can't just add them, doesn't work. I can't do a thrice this plus 2 this, doesn't work either. Do we all see that? That what you would have misinterpreted that there was a plus plus, hence you added it up, plus minus, subtracted it, no. What combination of these two gets rid of the omega 2 piece? I have the answer. If I multiply by 5, the first equation, add to the second piece cancels out. Okay? So u1 is 5x1 plus x2. Okay? And if I want to disappear the first piece and keep the second one, what do? Multiply by 2 minus 3 times second equation. First piece goes away. So u2 is 2x1 minus 3x2. So this piece only oscillates like cosine omega 1t plus phi 1 with some amplitudes, and this goes as cosine omega 2t plus phi 2. So these are decoupled oscillations. Okay? So I can maybe go for like a minute or so to kind of complete the loop. But now let's see the flow again. Equations of motion in particles. Write them down, Newton's laws, usual thing. Write them as a matrix. Double dots, column, n by n, here 2 by 2, equals the same vector itself. Conventionally define that matrix to be minus m, with the x double dot equals minus m times x. Find the normal modes. This last piece, the sing song. Special configurations for which each particle has the same frequency. Assume same frequency, omega, omega. Want to find the omega. Plug it back into my equation of motion. Omega squares are the eigenvalues of the matrix M. Solve for the eigenvalues. Solve for the eigenvectors. Normal modes are the special ones which have the same frequency as we just discussed. General solutions are linear superpositions of the two. And those special combinations of x1, x2 which decouple in the sense that they only have one frequency of oscillation are normal coordinates. Okay? So take a minute here. It was a lot that happened. Pieces might have looked very familiar. I know Eigen vectors, I know equations of motion, but this whole thing is not trivial. So please ask me questions about this. Next time, we're going to just do examples one after the other, nothing else. But please, questions at this point are very important. Whatever comes to mind, ask me, otherwise